here and share my screen and come over to our week 12 page here. This will likely be our last material that we'll need to cover before the final exam. Um, and yeah, I don't know, we probably won't use all the time today, but if there's lots of questions, then we'll use as much time as we need. Maybe before we get started, any questions on like administrative things? What to expect next couple weeks? Okay. So under here, the week 12 folder. Last time we sort of skipped over this hash index part. We're kind of going to skip over it today. They're not really used very much in practice. The reason for that is just that the B-tree index is so much better than the hash index for everything realistic. We saw before that the B-trees, they're logarithmic worst case access for everything, and the base on this log is super, super low. So in practice, we're only accessing like 2 or 3 pages. And the hash index goes from, just like a regular hash table, goes from logarithmic down to constant time, access amortized over all of the cases. This constant factor here, though, is typically about 3 or 4, the way it's implemented. And so the B tree, even though it has the logarithmic factor here, because the base of the log is so small, it's usually still results in fewer table page lookups. So because of that, it's very rarely used, this hash index. Sometimes can be marginally faster than the B tree, but only in very, very rare situations. And it has a lot of limitations on it. You can only do similarity search, can't do any of the equalities or the like operator, things that we saw with the B tree, does not sort the results. It turns out for weird implementation reasons, when you do a delete, you can't actually delete things from the hash table. And there's no support for index-only scans in the table, no support for multi-column indexes, and so on. So, so nobody ever uses the hash index. There's this reference up here to, again, to that Haber website, and in the true-false portion of the final exam, you might be asked something about the hash index that you'll have to look up here, but you're not going to need anything about the hash index for the free response portion. Any questions about hash index, what you need to know for that? Okay, the main thing for this last class today is more about the full text search. And again, last time we talked about the like, what does it mean to do full text search? That we're trying to speed up a query that looks something like this, where you have some text field and you're trying to find words or phrases that are embedded inside of that text field. And we talked about why the B tree can't implement that efficiently. The B tree can only implement it if there is a glob on one side of the search like this, and it can only work if it is case sensitive and not case insensitive. And then we talked a little bit at a high level about full text search stuff outside of Postgres. The main summary here is that if you're using Postgres, the advantage of that is you get your full SQL capabilities like joins, and the full text search in Postgres generally better than full text search in other relational database systems like MySQL, SQL Server, Oracle, but less good than these non-relational systems like where did it go? Elasticsearch up here. Elasticsearch is the most famous of the full text search engines right now. The disadvantages of using Postgres that we'll talk a little bit more about today, because there's the indexes and the tables are stored separately. You'll have to actually create the index, store the index. So it'll use about twice as much disk space. Things are a little bit slower for your inserts, updates, and deletes because you have to modify both the actual table and the index. But all of these sort of limitations here that exist for Postgres, people are working on removing those limitations. And so just like where relational databases used to not support JSON at all, and MongoDB was the best support of JSON. Now, relational databases like Postgres support JSON actually better than MongoDB, and you get all of the good SQL features. And so my prediction in say like 5 to 10 years from now is that Postgres will have all of the full text support that these other systems currently have that Postgres doesn't. And you'll still have the advantages of SQL. So that's why we're sticking in Postgres to talk about this. And for what you'll need for the actual final exam are the details of how to do full text search in Postgres and the details of the indexes. So in order to talk about this, I think the simplest way to do this is we'll just start with some examples and explain what's going on in the examples. So looking at our notes again, we'll start on problem 8 over here. I need to plug in my little pad to write with. And we'll talk about each of these problems and their solution, and then go into the details of the notes as it's appropriate for the problems here. Okay. So here, this problem 8 is saying that this above query is, it's doing a full text search. We'll talk about exactly what's going on in this full text search here in a little bit. But this query cannot be sped up using an index and why. So we'll investigate this query, see what it's doing, and then see why it can't be sped up with an index. And then part B down here is asking us to rewrite the query so that it can be sped up with an index and provide the actual index. So we'll do that as well. And again, this is exactly the sort of thing that you'll have to be doing on the denormalized section of the homework, where you're both writing the query and writing the index at the same time. So in order to talk about what's going on here, I have a terminal session opened up. I'm inside of the parallel assignment instead of the indexes assignment right now. And the reason for that is because there's less data in there, so I can create the index really quickly and get faster feedback on whether I'm creating the right index or not. If I run Docker PS right here, I have all of my 3 Docker services running, and I can connect with pSQL. We'll connect to the normalized batch one right here. Again, the schema that you'll get on your final exam will be somehow inspired by the normalized batch schema. Some subtle differences, but that you'll have to pay attention to for your final exam. But you can do all your tests on the normalized batch and make sure that things are working how you would expect. So we're looking at problem 8 right here. And then we'll break this SQL query down bit by bit, see what's going on. And so the first thing here is that we're selecting in this inner subquery here, we're selecting from the tweets table, and we have our text column, and we're applying a series of functions to this text column right here. Back over here, if we do \d of tweets, just to remind us what's inside of here, the text column is just text, and we can select text from tweets, limit 10. Let's just get us a sample of what these tweets here look like. They're in all different languages, we can see. So here's some Spanish, some German down here. Most of these tweets, though, really don't contain any actual text. They're just like app mentions of other user accounts or just lists of hashtags. It looks like we have some Arabic up here as well. And so let's just walk through. Here it is. No, that's not it. Here it is. We'll walk through what each of these functions are doing to process this text field right here. This first one, toTsVector. if we do select to TS vector, and then we'll just do this is an example right here. So not getting text from the the table yet, just getting text hard coded in like this, and we'll see what this function does. And what it's doing is it's extracting all of the important words from this string right here, and then putting them into this type called a TS vector type. And so here, the important words are, or these are examples of non-important words. This is an, just because they're very, very common words, things that you don't really care about in your search results, but example over here is an important word. And so it is, it comes down here. And stored in the actual result. You can see over here that the word here, the suffix, the ending part of the word is taken away. And the reason for that is so that we can, if we have, this is an example or something like these are examples, both example and examples will be stored in the same way inside of the TS vector without the ending part of our word over here, so that when we end up doing a query, we will not have to worry about whether about things like parts of speech in our query. So this TS vector, toTS vector function, it's doing two things. It's eliminating these sort of meaningless words, and when it tokenizes these other words, that it removes suffixes so that words that have the same sort of root will get stored together. So example and examples, both being stored in the same way. In both of these examples here, there's only one sort of meaningful word, but if we have now something like CS 143, or the final exam in CS 143 will be really hard, then there's a lot of words down here all being stored, all of the sort of meaningful words up here, whatever Postgres determines is meaningful, getting stored down here, and all of these filler words not being stored down here. This processing is a language-dependent processing, and you can specify the language by using a different version of this TS vector function, a 2-parameter version. The default on our installs of Postgres is English processing. So here, doing all the processing with English. This version of the function up here is exactly equivalent to this function down here. If we don't want to do any of this pre-processing, then we can put in simple right here, and it will store all of the words exactly as they're written up here without doing any of the tokenization or removing of the simple words. So that's just what the toTS vector function does. It's sort of reformatting the text in a different way that will be useful for search later on. Any questions so far? The next function in this problem is TS vector to array, that we've seen how to do various searches with arrays before. And we, in particular, combined our arrays with this unnest function. And so if we apply the TS vector to array to the result of our toTS vector, then it's just going to change this, the type of this, the way this information is stored from the TS vector type to this array type. And the thing about the array type that we've used before is this unnest function, which is an example of a set returning function. Unnest. And set returning function is, again, one that returns multiple rows for each row of input. So here we have one row of input right here. And this pattern of converting it to a TS vector, then converting it to array, then converting it to an unnest will give us one row in our output down here, one row in our output for each word in our input over here. So the idea of this whole inner query right here is that we're going to have our id tweets, and we're going to have next to that an individual word, where that individual word is all of the words that corresponded to the text for each of those tweets. So if we write that out, select id tweets, comma, that whole big thing up here, simple, comma, text, and 3 closing semicolons from tweets. This further out of the way. From tweets, I think that's it. Let's add a limit 10 here so that it runs quickly. We can see that here is the first tweet. This text right here corresponds to the first tweet. I know this is the first tweet right here because these ID tweets right here are all the same. And then the first tweet ends and the next tweet starts down here. And this is all the information from the next tweet down there. Can make this a little bit more informative maybe if I add the actual text column here as well. This is now different than the query in the PDF file, but here you can see that this right here is the text of the tweets. It's the same in each of these 3 lines right here. And then this Quimby, Sh, and Sven correspond to the these 3 tokens that have been extracted out here from the text. What our final query then is doing, it's going to try to select everything from there, do a filter on here where the lexeme just equals whatever it is that we're actually searching for. So lexeme, just like a fancy word here for word. So searching for tweets that contain the particular word that we're searching for. I'll do \E to edit this in Vim, select star from this subquery where, and I need to name this as lexeme, where we'll do something like lexeme equals corona, like that. Save that. I have an error. My limit \E. There's a semicolon up here. Close that. Save that. Run that. And now we have 44 rows. I press Shift G in my pager environment here just to count how many rows there are. G to come back to the top. And so there's 44 different tweets that mention the word corona inside of them somewhere. And we can see that these are the corresponding text over here. So there's corona here, there's corona down here, and so on. So we're doing, so it's full text search. We're finding the word corona anywhere inside of this tweet. And that's what this query is doing. That's what this query right here, this whole thing is doing, is a query for full text search where the term that we're searching for is specified as this lexeme right here. Questions about why that's doing full text search or what the query is just doing? Okay, then so the part A question right here, the query above cannot be sped up using an index, and why? There's sort of multiple ways to answer this. The first point here is that we have a anytime we're running a or anytime we're using a query, in order for a query to filter out something on the where clause down here, we need the thing that's to the left of an equal sign or to the right of an equal sign, the column that we're indexing in our where clause. We need a index to be built up off of this column right here. So we would need an index on lexeme. We need an index on lexeme, but lexeme is, there is no table in the database that has lexeme as a column. What has lexeme as a column is this, this subquery right here. Lexeme is a column of the subquery. And you can't create an index on a subquery. In general, the only type of relation that you can create an index on is an actual table that has sort of a global universal scope and is not defined just temporarily inside of another query. So that's the first explanation of that. Another explanation is that we could potentially maybe rewrite this query in a different way, where there was something down here that we could index. In particular, we would like to have an index built over this entire thing in red right here, because this is what our lexeme is. But unnest right here is a set returning function. And you can't build an index on a set returning function. On set returning function. So these two things combined together is the explanation here for part A. In terms of grading, if a problem like this was worth 4 points, then you'd need to have both of these explanations here to get the full credit. If you only had like part of the explanation, either the blue or the red, then it would probably be like a 3 out of 4 on the problem. But yeah, so it needs to have the full explanation of both of these two things in order to get the full credit. Any questions on? Yeah, no?
I vaguely recall you mentioning something about like there's a variable, like a user variable
So let's see. What can we create indexes on? So here, number 3 up here, we have this function over here, function username. And this function over here is not set returning. And so it is possible to create an index on this function over here, and it would look something like this. And this is allowed because lower is not set returning. For every one thing as input, it returns one thing, exactly one thing as output. So this is allowed. And this is what the corresponding index would look like. If this lower was to the right of the equal sign, and so the query looked like this, where lower had the user input as the parameter, then our index would look like we would not need to put the function inside of the index because this thing needs to be evaluated only once. And then what we're comparing to actually in the index is the username column over here. And so our index would just look like users parenthesis username. I have it crossed out right here because it turns out we already have this index. It's a unique index on username. And so there's no need to create a new index down here. Did that answer your question? Problem 8. Okay, so part B down here is asking us to rewrite this query so that we are able to use an index. And this is where we'll get into how to build indexes for full text search. The way to do that is that we're going to use, well, I'll write out what the correct query is going to look like. Then we'll talk about what the query is doing, and then we'll talk about the index to speed up that query. It looks like select, so id tweets, comma, text from tweets, where, I'll end this, go into the into Vim here, where 2ts vector text at 2ts query, whatever our search term is, corona, like that. And this will be the query that we'll use to do the full text search. Here, this at operator, this is the semantics of this is saying if the thing on the right over here appears anywhere in the thing on the left over here. Most of the operators that we've seen are not order dependent, like the equal sign in Postgres, not order dependent, but the at operator is, it matters to have the thing that you're searching over on the left-hand side and what your query is over here on the right-hand side. And if we run that, then you'll see that we still get this same 44 rows down here as the output, still get the same text over here that we're searching through, like Corona right here and Corona right here, still finding all the tweets that mention Corona anywhere inside of them. So this at operator, again, is equivalent to doing that long chaining of unnests, but it's both easier to write, and we'll see that because now the there's just a single function over here, it's something that we will be able to write an index for. So yeah, over here, I'll go ahead and write the query out. Here, it looks like select id tweets text from tweets where to ts vector. And I'm actually I'll leave this empty here for a second. We're gonna talk a little bit more about what's gonna go inside of there in just a second. And then to ts query, I'll leave that empty here for now as well. So this is what I just had inside of Postgres, inside of pSQL that I typed in, with the exception that I'm temporarily leaving the stuff in parentheses to these functions empty, so that we can talk in more detail about what goes on inside of there. In order to in order to talk about that, let's take a look at, or what I want us to do is to see how we can create an index for this, and then we'll see if we have to modify anything inside of these parentheses in order to create that index. Before actually creating the index, I'm going to turn the timing on. So again, this is a good debugging command as you're working on the homework assignment, just to get timings for everything. And so here the timing takes about a half a second to run this query when there is no index at all. And again, I'm using the parallel assignment instead of the index assignment at this point, just because there's only 10,000 data points instead of 30 million. So like a sequential scan over the tables, relatively fast to do. If we change this, if I add the explain up here in front, you'll see that it's still doing the sequential scan. And you can see it's actually chosen to use 2 parallel workers here in order to do this sequential scan to speed things up. But my goal is to change this from a sequential scan to some sort of index scan in order to speed up this query. So anytime we have or the only times that we can use an index to speed up queries are when we have one of these where clauses right here, and we have an operator, and we have to create an index specific to this operator. The at operator does not use a B-tree index or a hash index. Turns out there are 3 types of indexes that we can use, and they're all listed down here at the bottom of this README file. This index is for the at operator. There's this gin index, and a rum index, and a gist index. And I'll start by going through the code of how to create them inside of pSQL. Then we'll talk about exactly how they're different from each other. So down here, in order to create the index, it'll look like create index on tweets using Gin. The new part right here is this using Gin that was not previously in our commands. This part right here, not previously in our create index commands, but by saying using and then the name of the index type, we can specify the type of index to be used. So anytime you're doing the full text search, you'll have to have this using and then one of those three other index possibilities right here. And then over here on the right-hand side, we need the column that we're searching over is this column right here that appears to the left of the at sign. So the 2TS vector text like that. We can't index directly onto the text. We have to index onto the TS vector output of text right here. And if I do that, we'll get this error message down here saying functions and index expression must be marked as immutable. It turns out that this 2TS vector, by default, the default language is whatever the system language is, and the system language can change. And so this is an example of a function whose output will be different every time we run it, depending on some external factors. In order to make this an immutable function, one that never changes, we have to explicitly specify the language over here that we're going to do that tokenization process with. And if we specify this, then we will be able to create the index. So it takes 2 seconds or so over here to create the index. And now we can do that. And now we have the index available. If I come back up here and redo my explain operation right here, we'll see that it's still using a sequential scan on tweets though, because my condition over here, my condition to the left of the @ sign does not exactly match the condition inside of the index column up here. When I have Gin, I have 2TS vector English text. This happens to give exactly the same results right now for 2TS vector text, but because these two things are not exactly equal to each other, Postgres doesn't realize it can use the index and it does not use the index. So to fix that, we have to change this to specify the index right here. And if we do that, then you can see now it's doing a bitmap index scan on that index instead of a sequential scan. And so if I take away the explain and actually run this query, then it happens very fast and less than half a millisecond. So we got 1,000-fold speed up there, going from 500 milliseconds to less than half a millisecond by creating that index. So the final answer then for this problem over here is that on our create index command, it looked like create index on tweets using Gin, and then inside of parentheses 2TS vector English and text like that. And then our TS vector up here, we have to first provide the English inside of there, and then over here, just the text. For our TS query over here, you can see that that's when I ran my select statement up here, I did not specify that the TS query language, I didn't specify that manually. You can, though it's recommended that if you're specifying the TS vector manually, it's recommended to specify the TS query manually as well, and you'll get the same exact results, whether you specify that or not. So over here, it would be recommended to put English, and then your colon, lexeme right here. And this upper English and TS vector required, this lower English and 2TS query, this one right here, that would be optional. You don't, whether you include that or not, either way is full credit, but everything else would be required. Questions?
So when you put in this English part, it like changed the immutable there?
Yeah, so the concrete reason why we had to put in the English in our create index on tweets right here is because without it, we're getting this immutable error, and then with it, we're not getting the error anymore. The reason why that's the case is because 2TS vector, the language that it uses to do the that stemming process and the tokenization, the language that it uses is whatever your system language is configured at, and the system language could change, and it doesn't like the fact that the system language could change, and so it forces you to manually specify the language down here. Turns out, so Postgres has support for about 30 languages built into it. All of them sort of like European languages. There's extensions that you can install to Postgres that makes it support non-European languages. But by default, it only supports like English, Spanish, French, Russian, European languages, just because those are easy to do that pre-processing step with. Other questions at this point? Okay, then we'll talk about how this GIN index is implemented next, and the differences between GIN and some of the other index types, and the limitations of GIN compared to those other index types. And so for that, we're going to be on the README file down here under this indexes for the @ operator. There's these two references that we'll be looking at, the one for the GIN index right here, and then eventually the one for the RUM index down here. So this is the documentation for the GIN index. And up here, there's a create table command, just storing some information in the table inside of a text field. This doc column is a text field. And then they're running the 2TS vector function on that doc column. So in our example, the index was being created on a it had a function inside of the index column right here. In this example, they have an additional column over here, this doc TSV, that is storing the TS vector type directly. And they're putting this information inside of the doc TSV right here with this update command, and then building the index on the doc TSV. Turns out that it is doing the same thing. This method used to be what you had to do inside of Postgres, but it's storing one additional layer of extra information, directly storing this TS vector on the hard drive. And so it's not as efficient as this of storing the TS vector directly in the index like this. But it's maybe a little bit more explicit, so that's what they're doing in the documentation here. And then down here in the figure below, they're showing what the format of the GIN index looks like. GIN stands for a generalized inverted index. And what an inverted index is that it has, it's basically like the index at the back of a book, that every word in your document, as determined by the TS vector function, every word in the document gets inserted into a B tree structure. So here, these all of these circle-ish rectangles correspond to all of the words in the document. And then every row up here that matches one of those words has an entry inside of this black entry down here is the entry that corresponds, this is a row, the tuple ID number, the first one being the page, the second one being the tuple in the page that corresponds to the row that contains the word could. So could is only used in one row. Let's see up here, F. Could is only used in one row right here. And so because of that, we only have one of these tuple IDs underneath could. If we look at the word sit, sit is used in two different rows. And so we have two different tuple IDs that contain the word sit. So control up here, sit, sit's used right here. Sits with an S at the end is down here, but because of the tokenization process, the suffix is taken away. And we just have sit stored twice for both of these two rows. These, for small numbers of tuples, these are called posting lists that the lists of tuples are stored in. But as the number of tuples grows, the tuple IDs end up getting stored inside of a B tree structure like this, called a posting tree. So the word slit appears, I think, in every one of these rows up here. Slit appears in every one of these rows. So every row matches slit. And so it stores all of those inside of this posting tree structure down here. Any questions about the format of this GIN index, generalized inverted index? Okay. Then, yeah, when you do a search for just a single word, it's going to return either the posting list or the posting tree that corresponds to that individual word. A nice thing about the TS vector, this syntax down here, is that the query can support not just individual words, but has relatively complicated query syntax where you can search for do arbitrary Boolean operations and things a little bit more complicated than Boolean operations. So let's do corona and virus like this. Individual, and there we go. So corona and virus, there are, here's our index scan. Let's take away the explain. There we go. So here, there's now only 4 results down here that contain both the word corona and virus. In this case, all these results, corona and virus, appear right next to each other, but there's no restriction that they had to appear next to each other. If we really wanted things to appear next to each other, then this syntax says the word virus must appear immediately after the word corona. And so that gives us the exact same matches in this case. We change this to virus and corona, we still get those same 4 matches because the order down here doesn't matter. But if we change that to the sequencing operator like that, then we'll get no matches because virus never occurs immediately in front of corona. The way the way the GIN index handles these complicated queries is it does a bitmap index scan. Anytime you're doing a index scan on a GIN index, it's always going to be the bitmap scan that it's going to do. And it will combine for each one of those query terms. So if we did, say, slit and upon, it would get our posting tree for each of those terms and then do the appropriate bitmap operator to combine those posting tree and posting lists together. So the reason why this is stored as a posting tree down here is because it makes doing those bitmap operations fast on each other. So summarizing, the GIN index here used for full text search. You can also use it to index the JSON-B or arrays, anything where you have many components inside of something else. The limitations, if you're deleting things from a GIN index, You can never, the GIN index will never update this upper B tree structure. So if we were to delete a line that contained the word could would never be deleted from this B tree structure up here. We would only delete the black part down here. The posting list would become empty. That's a pretty minor limitation, but it is a limitation. It's slow to modify because in order to insert a new document into the B tree index here, you're going to have to insert, if we consider this document right here, if we insert this, we have to insert many different elements into the B tree index. We have to insert she and slit. We'll skip the insert sheet and insert sit. So there's 5 or so different entries that get inserted here. For large documents that are like megabytes in size, that can result in a lot of things being inserted at once. It does not store any auxiliary information. So we've seen before that we could create multi-column indexes to say only do an index-only scan. That's not possible with the GIN index. So in particular, it does not store the location that lexemes are stored at. So the GIN index is fast for a query like this. It's fast for a query like this using the Boolean operations. Both of those are fast, but it is going to be slow for a query like this because this will first perform an AND, but then it'll have to also reevaluate the entire documents and check to see if those words were actually right next to each other. Does not support the index scan or the index-only scan and only supports bitmap scans. So this implies that the limit operation will not be efficient and we cannot sort the results of a GIN index, and we can't do this thing called clustering on an index if we needed to. So those are the limitations of the GIN index. The RUM index fixes all of those limitations. Again, here's the reference for you. The explicit motivation, yes, question.
Does that mean purposely?
It is, yes, explicitly named purposely. The GIN index up here, in the documentation of Postgres, they specifically say that GIN was not inspired by the alcohol at all. RUM down here, though, the creator of the RUM index says that rum is better than gin in alcohol in every possible way. And so he called this index the rum index because he thinks this index is better than the gin index in every possible way. So it can do everything the GIN index can, but it also lets you store meta information inside the index itself. So things like page ranks or timestamps, other things that you would want to be filtering on in your search query. If we come over here, this is what the sort of pictographic representation of the RUM index looks like, that the B tree at the top is still exactly the same, but now in the posting list or the posting tree, instead of only storing the tuple IDs, it also stores whatever other information that you want stored as well. So it can make queries that require that auxiliary information faster because it can do an index-only scan without having to inspect the table. And because we can do an index-only scan now, or an index scan, speed up from fewer pages accessed, and you can use the limit clause, and the results can be returned in sorted order. So a lot of advantages here to the RUM index. The main disadvantage of the RUM index is that it's not built into Postgres. And so if we come back to my create index, the syntax for creating it is just doing this, changing gin to rum like that. But these Postgres instances do not have the RUM index installed in them, so you can't actually use the RUM index here. I thought about, or in the past, I've made students in the index homework install the RUM index and use the RUM index, but in this case, I have, or for this semester, I've decided not to make you all actually install the RUM index. So you have to know about it for the final exam, but you don't have to install it for the homework. Going back to this problem 7b right here, if you were to, instead of saying a GIN index right here, if you were to say a RUM index, that would also be a full credit answer, and this would actually be the the faster answer, the better answer, because you have that index and index only scan options available. Any questions about the difference between the GIN or the RUM index, or what you need to know about each of those?
Not about the difference, but
sure.
when you're typing the stuff inside of the TS query, why is it that put like the Boolean operator inside? Why did they do it?
Question is for the 2TS query right here, why does this go, like why is this the format of the query?
I think it would make more sense to have like the string binaries and then the operator and then the string program, but it's all
yeah, so the question is, let's say instead of something like this, why don't we have something like this, or to use the same operator, something like this? And the answer is because of, again, this SQL language is from the 70s. At the time, people didn't know how to implement like polymorphism like they do in modern programming languages. And so here, if we were to type this out like literally like this and do Postgres, what it's interpreting that as, this is the Boolean and operator and combining two strings with the Boolean and operator, and it doesn't know how to do that. So the sort of the right way to think about this is that actually this is its own separate programming language, which is the query language for the TS query. And it's totally independent of SQL. And we pass that code for the query language into this function over here, which is like a compiler for this language. And then it creates the resulting query type, which is then represented this way with the words outside of the quotation marks. And that's what's passed to the at operator. But yeah, it's just an artifact, or the reason it's this and not this is just an artifact of how SQL has to be implemented and conformance with the SQL standard. Turns out currently there is no SQL standard at all for full text search in any database in any way. And that's because all of the databases are currently doing something totally different. And nobody knows like what, or there's not really anybody who's thinking about making the SQL standard updated with full text search capabilities. It's all just on a database by database level right now. Good question. Any other questions? Okay, let's come over here and scroll up and take a look at problem 7. So problem 7 here has us doing full text search again on the tweets table on the text inside of there. And this query is a little bit more complicated than the one we were working with before. And so we're going to write an index that's going to actually speed up a query like this. We'll start by thinking about how to do this without these 3 lines down here, and then we'll update the query to take into account these 3 lines. So the top part of this looks basically like the query that we had before, and so it would be something like create index on tweets using RUM. I'll do it all with the RUM index now instead of the GIN index. And here it'll be the 2 TS vector of English text like that. And that's everything that we need in order to speed up just these first 3 lines up here. And I guess technically this 2TS vector right here, we have to specify the language in order to speed this up. So that would need the English language specified right there as well. Any questions on why this red part here is a query that will speed up that up there? Okay. So now let's take a look at the other condition down here where we have more columns, this created at column, and we're trying to filter on the created at and order the created at. This ordering operation here is like a distance operation. How far is created at from this? So it's not like not a less than and greater than. It's like a distance. So it's the distance from created at to the beginning of January 2020 distance from the date. The and clause up here is filtering so that all of the results that we get will have been created after January 1st, 2020. And so the distance from that date will correspond to ordering the dates from oldest to newest. Both of these two lines together implies that the order will be from oldest to newest. And it turns out that this is the only that you have to specify something like this in order to get the speed up with the rump index in order to when you're ordering by things. In order to make this work with the RUM index, in order to take advantage of this extra information, we have to add it into the index itself down here. So I'll put the created at right here. And unfortunately, this is, so semantically, what we want to have happen is that this created at will be stored inside of these sort of gray boxes down here, where it's the auxiliary information that's stored about each document next to the tuple ID in the posting list or the posting tree down here. In order to make that happen, there is some obnoxious syntax that we're going to have to write, and I will write all of that obnoxious syntax here in green. The first thing that you have to do is up here, add this extra flag saying rum underscore TS vector underscore add on underscore ops. This is all one word right here that's to the right of the TS vector, and then a comma after that, separating these two columns from each other. And then after the parenthesis over here, there is a with and attach equals created underscore at 2 equals 2 underscore TS vector with the English, comma, text. I think I got all of my parentheses matching here. And syntactically here, this string inside of the to operation contains single quotation marks inside of it. And in order to escape those single quotation marks in SQL, the way to escape quotation marks is you put two quotation marks next to each other. So this is not a double quotation mark, but an escaped single quotation mark. And yeah, reasons for needing all of this extra stuff that's in green are historical for backwards compatibility with the GIN index. That documentation on the Haber website goes into exactly the gory technical details of what's going on. But for the purposes of the final exam, you just need to be able to reproduce something that looks like this if you're choosing to create a RUM index instead of a GIN index for the particular problem. And you have to do that again when you're trying to store a second column in this extra piece of information down here. And you're trying to do that if there is another column that is incorporated into the where clause or inside of an order by. Any questions on that? No? Correct. You only need all of this stuff in green if you're creating a multi-column RUM index. Multi-column B-tree indexes do not need this, and single-column RUM indexes do not need this. All of this stuff in green and this orange right here, that takes into account the and the order by clause, making them go faster, making it so that we can do an index only scan on the tweets table right here to complete this query. And because we're able to do an index only scan, that means that the limit clause here will also be something that we can speed up. And again, it's the RUM index that allows us to do an index only scan. An index only scan is not possible with a GIN index under any circumstances. Any questions on part A there? Okay, then part B, assume that you're unable to install the RUM extension into the database for some reason. So then how would you change your answer above in order to get the fastest possible query? And the answer is that you're no longer able to do the limit by clause. You're no longer able to take advantage of that or to take advantage of anything inside of this X. The only thing that you can take advantage of is this @ operator up here. And so just writing the index up here that I have in red, but with a GIN index would be the best possible thing. Using now GIN to TS vector English, comma, text, closing parenthesis, like that. Any questions about that? Okay, that's everything that we're going to go over for the final exam. There are, mentioned this before, up here in our repository. In this final folder, you can see the previous final exams and answer keys. I recommend going through those before doing the final. And sometime, which I don't know yet, but sometime before I give you the final, we'll have another class period that'll be a final review session where you can just ask questions about why these answers are the way they are for each one of these finals. And then after that, I will post the final exam and you'll have a week or so to work on the final. Any questions about anything? No? The final exam, you'll have unlimited access to computing, basically just like the midterm. So you can test your queries as much as you want, um, just not talking to other students. I think the actual, I believe the final PDF here that I have posted has the actual detailed rules of what you're allowed to do and not do. Yep, so take as much time as needed, use any written notes, use the Lambda server, ask me to clarify questions by email, just not talk to other people. Okay, then that's it for today, and see you all at final review session, probably end of next week or maybe early week after.